Hi, and welcome to our seventh tutorial of pm4py. In this tutorial, we will be looking at process discovery. Yeah, let's go straight into the topic. So in general, today, after I will briefly introduce again what process discovery is, for more in-depth overview, conceptually, I refer to the first tutorial video. Today we're going to talk about discovery of various different types of models. So BPMN models, process trees, Petri nets, and process maps. And for each of these different types of models, I'm also going to briefly indicate to you how you should read them or how you should infer them. Finally, I will briefly talk about how to handle noise from within the process discovery algorithms. And some final thoughts in general about process discovery, where we are right now, at least from a more academic point of view, and challenges that are still open. Okay, so to recap, I'm going to use a running example throughout this presentation and constantly going to use event data and models that reflect basically the process that is described here. Now, this process, you've seen it before because I'm always using it as a basic example. The idea is that this is a process that describes requests for compensations. For example, if you went to a concert and for whatever reason you couldn't make it, you want to get your money back, this type of compensation, type of requests. So how we read this model, this is a BPMN model. How we read this model is we look at the starting point, which is indicated here as a circle, and below it's written start. I will also highlight that in the slide. So this is the starting point of our model here. Now, and we're going to basically follow the arcs that are there. So from this specific starting point, there's only one specific arc here that I can follow. So and then we see that there's a register request activity. So what we deduce from that is the first activity here is a register request. And then if we traverse the arcs further, we get into this diamond structure with a cross in between. And that actually indicates that there's a choice. And in this case, the choice, or let's say there's multiple ways in which we can enter this specific choice point. So we can either come from the left, that is after we have executed the registration request, or we come from the reinitiation request. But this is an activity that is only executed later. So in the current, I was currently coming from the register request activity. So first activity in this process is a register request activity, and then you might alternatively come into the same routing point. You can look at it like that, this diamond with a cross inside. You could alternatively come there via the reinitiate request activity. Now, if we then again proceed from our choice point there, we enter another diamond with a symbol inside. This is a diamond with a plus. That is the element over here. I'm highlighting it now in green. And this is a very important sort of operator because it tells us that from that point onward, there is concurrency. So if you see such a diamond with a plus inside, it means that actually when you would basically need to split up yourself in two. You should clone yourself in two and start walking both outgoing edges, in this case, both outgoing arcs, because everything that can be reached from an outgoing arc there can happen at the same point in time. So that means that we can at the exact same point in time walk the lower arc and get into the check ticket activity, or we can go up and we get another choice point. And there we see a choice point saying, well, in this process, we either examine the request thoroughly or we do it in a casual manner. So this is a choice. So we always do one of these two, either a thorough check or a casual check, casual examination. And we do that concurrently with the check ticket. So it means that some other resource might check the ticket while we do the examination. In certain cases, I might do both, and I might first do one and then the other. So basically in this BPMN model, you can infer that in both ways, but basically it can happen at the exact same time, or you can schedule it in any order. So if we then proceed in this model, you observe that at some point after you've either went to the examine thoroughly or you went to the examine casually and you've done the check ticket, you end up again in a diamond with a plus. And that specific diamond with the plus here is a merge point of the diamond with the plus on the left. So it says, okay, here you have to basically wait until all the incoming edges of this diamond are satisfied. So we have executed one examination, a thorough or a casual examination, and we've done the ticket check, and then we can proceed. And actually, if you look closely, you see that the choice point here is actually the join point or the merge point of the split that we see here, right? So in this model, you actually observe that there's these split join combinations. What we see then is that we can again continue our process and we can get a decision. Again, we end up in a choice point, and here choice point has three options. Either we pay the compensation, either we reject the request. Maybe there was something wrong when we were handling the request and we decide to reinitiate the request, which leads us to end up again in this merge point that I've already discussed before. So basically that's how you should read this BPMN model, and I'm going to use that process as a running example. So we're always looking at data that we presume that comes from the execution of an information system that supports exactly this process. That's what we're going to look at in the presentation, the remainder of this tutorial. And as you know, in process discovery, what we do is we look at this type of event data that we've seen before in the various tutorials, and we try to discover automatically process models such as the model that I've shown you in the previous slide. Again, so if I take the running example data set that you can also find on our GitHub page with the accompanying notebooks that we have, where you can read through the material I'm presenting here today. You see an example of a event log that captures historical executions of the process that I've just described. And if you take a careful look, and let's take a look at the first few rows, they all refer to some request that has an identifier value of 1. I'm not going to go into too much detail of this event data because I've done that in previous tutorials. So please take a look at those if you're no longer or not familiar with that. What we see here is that the first row describes an activity for a request with identifier number 1. That is a registration of the request, followed by an examination, a thorough examination, then a ticket check has been performed, then a decision is made. So up until this point, everything is in line with the model that I just described, because I hope that you remember vaguely that we started with the registration of a request, and then we had actually this parallel block of, on the one hand, doing a check of a ticket, and on the other hand, doing an examination, which was either thorough or casually, and after which we make a decision, which is exactly what you see here in this table. And finally, in this case, the request was rejected. Now, if we look further in this table, we see that there's another request being recorded, and that's the one over here. That starts with a registration. Then we have a check of the ticket, and then we have an examination. Now, and I want you to focus explicitly on this block, because here we see that the ticket check was executed before the casual examination. Here we see that the ticket check is actually executed after the examination. So, and also the examinations are different, right? There's a thorough examination for the first case, and there's a casual examination for the second case. Now, if you look closely at this log, and I will later in this tutorial spend some more time on discussing this, you see that for every event that we record, so for every row that we record, which represents the recording of an activity that has been performed, we observe that we only have one timestamp. So you could say, okay, maybe every timestamp in this table refers to the completion of the activity, right? So for the first event that describes the register request activity at the 30th of December 2010, maybe that was, or not necessarily maybe, but that was finished, for example, the registration at 10 a.m., 2 minutes after 10 a.m., right here. So, and the point is that even though in the previous slide, I've shown you a process model where I said this can basically happen at the exact same time, because we only record the completion times, even though these activities might have overlapped in reality, if we only record the completion times, we cannot see that because we only see one point in time, the completion time. So that means that if you model something or if something happens concurrently, but you only have one atomic timestamp in a way, or you have one point in time where you observe that activity occurred, so you don't have a time range, but you have a single point in time, you can only see the interchange of those activities. If they happen, of course, at the exact same point in time, or they complete at the exact same point in time, you would actually see that they happen at the exact same point in time, but then again, we would still show them in some order in this table. Anyway, to proceed for this second case, which I'm highlighting in blue, is after the casual examination, so check ticket and examine casually have been performed, a decision is made, and in this case, the compensation payment is being executed. So you see in this example, both are valid executions of this process as described by the model. However, there is various differences, like there's a different type of examination and the ordering of the examination versus the ticket check is actually different. If we then go to, let's say, another example case, another example trace in this data set, we see here identified by number 3, we of course also start with the registration request and an examination that is casual, and then check ticket. So in a way, you see that the order between the examination and the ticket check is the same as in the first case, right? If I look at the order of the examination and the ticket check, you see that the examination is first, and then the ticket check occurs, but the examination type here is a casual type examination. After this first round, we see a decision, and apparently there was something wrong in the check or something wrong in the examination, and there was a decision to reinitiate. And in this case, we see a thorough examination. We do not see a casual examination. We see the ticket again being checked. The decision is being made, and finally compensation is being paid for this specific case. Again, this is completely in line with the model that I showed you in the previous slide. Now, the goal of process discovery is simply to take such a data set and try to find a process model such as the one that I've showed you before. However, there's one major difference between the current situation where I'm explaining you everything along the lines of a given process model, because normally when you extract this type of data from an SAP type of system, an ERP system, or Oracle database, or Salesforce, all these different types of systems, if you extract this type of data, you don't know how the process looks like. You don't know what the process looks like. You do not have a model that represents the behavior of the process. So here in this explanation, I can constantly refer back to the model that I've shown you before to explain stuff. In reality, you do not know that model. It doesn't exist. And that's the big challenge. Now, in this tutorial, I'm going to show you various ways in how to discover process models, such as the model that I've shown you in the example, using this running example data set. I will not go into too much theoretical detail about how these algorithms work. I can explain that. At the same time, there's already the online Coursera course on process mining where you can find this information. I would say if there's people that have, let's say, would like to see a more in-depth explanation of certain algorithms, then type it in the comment section and we can make a dedicated tutorial for that as well. All right, so we start off with discovery of BPMN models. That's our first goal. And actually, that's super simple in pm4py, because what you can simply do is you can say, you can use pm4py dot discover BPMN inductive, and you apply that on your data frame. So the general terminology in that sense of pm4py is that, of course, you indicate that you want to use a discovery algorithm, which you just indicate by writing discover. Then we have an underscore, and then it is actually the target type of model is listed. And finally, you see some reference to the underlying algorithm that is used. There are various algorithms that can discover different types of process models, and that's why we do it like this. You can choose to either input a data frame that you formatted in the way that I've shown you in previous tutorials, or you can use an event log. So if you have a access file that you've imported, you can also give it to this function. The function will automatically detect which input type it receives, and based on the input type, it might convert one to the other, or in certain cases, we actually have two implementations, one for data frame-based storage, one for event log-based storage. And pm4py also has a view underscore BPMN function, which basically allows you to view the model. You can also export it to disk. That is pm4py.export underscore BPMN, but it makes no sense to demo it. It's pretty straightforward. So if we use the data frame that I've just shown you, and we learn the process model using pm4py, you get the model you see in the bottom. And you might already notice that this, okay, of course, the visualization is different, uses a different algorithm, different underlying library to visualize. But in the end, this model actually resembles the previous model, right? And for convenience, I'm showing both of them on the slide here. And observe that both say, okay, we start with the registration request, and then there is some merging, right? There's a merging between coming from register request or the reinitiate request. After that, we see parallelism, and we see exactly that there's a choice construct between the examine thoroughly and examine casually activities, and there's a ticket check. We can then finally make a decision. And after that, we see that there's a choice between the initiation of the request or the rejection of pay compensation. The only fundamental difference, but it's not really such a fundamental difference, is that somehow the algorithm that is in pm4py decided to split up the final choice. So you should infer this as after the decision, one either reinitiates the request or one proceeds. And after proceeding, one has another choice between the rejection and the payment of compensation. That's the only difference. But if you would, let's say, exhaustively generate all possible sequences of process behavior that you could think of that eventually end up in the endpoint of this model, right? That eventually end with a rejection or payment of a compensation. The languages, that's what we call that, the languages of these two process models, BPMN models, is exactly the same. So you can use what is known as the inductive miner in pm4py to discover a BPMN model, but there's a sort of a catch. And that's why this this next section, I'm going to talk about discovery of process trees, because this inductive mining algorithm, and as I said, I'm not going to explain it into detail, but what it actually does in a nutshell, it looks at the event log, it computes an abstraction, which is known as the directly follows graph, which actually often also used as a process map in commercial applications. And what it does on this process map, it tries to smartly discover whether there are certain patterns that can be detected. So for whether, for example, one can detect that there's actually sequential behavior among certain groups of activities or concurrent behavior among these groups of activities. And when this algorithm finds such a behavioral pattern, it's going to then actually apply itself. And that's why it's called the inductive miner, because it sort of recurses in itself. Going to recursively on the subgroups that it has detected, is going to apply itself. So it recursively finds possible behavioral structures. And because it does this recursively, and it does some smart way, if something, if no structure can be found, it will return some sort of, I cannot find anything type of structure. That this has let's say, the output is actually has a hierarchy and can thus be represented mathematically as a tree. And so the point is that this discovery algorithm actually discovers what is known as process trees. And process trees are trivially translated to BPMN models. So it's very easy to translate a process tree into a BPMN model. There's nothing difficult about it, because the types of behavior that this process tree can represent, and actually what the inductive miner can find, are a strict subset of the types of behavior that you can find in BPMN models, or Petri nets for that matter. So you can also directly discover process trees with the inductive miner. And obviously, the semantics for that are very clear and very similar to what I've just described for BPMN models, right? So it's, again, you type pm4py dot discover underscore process underscore tree, you discover the object underscore inductive, because you use the inductive mining algorithm to find it. Again, if you want to check it, how it looks, you can type pm4py dot view underscore process underscore tree, or if you want, you can export it. Now, what's important is I'll try to explain how you should read this model. And I'm going to do that actually by comparing the process tree on the top with the model on the bottom. So first of all, this is a process tree, and for the mathematically inclined, this is just mathematically speaking a tree, but every internal node and every leaf has an associated semantical label. The internal nodes, so those are nodes that are not leaves, meaning those are nodes that have at least 2 or more connections. So that these are all internal nodes, because if you look closely, you see that each of these nodes has 2 or more connections. Now, these internal nodes, they are called operators. And it means they are actually describing behavior. And there's actually only 4 types of behavior that we have currently in these types of process trees in pm4py. There's sequential behavior, there's choice behavior, concurrent behavior, and looping behavior. Sequential behavior is represented in this tree by SEQ. So if you look at the top circle here, the top node, which is also known as the root node of this tree, that's a sequential operator. And a sequential operator should be read as follows. Okay, there's sequential behavior from left to right. So first, to inspect its behavior, first I need to assess everything somehow that happens here. If I've done that, I need to assess what happens here. And finally, I need to assess what happens here. That's what the sequential operator explains. If you would translate that into the underlying model, you could think of it as follows. It's kind of like saying, first we start, and then we have to finish this block that contains on the left of this line here, the register request. And then we somehow have to continue a bit more, and we have to do a bunch of stuff in the middle, and then finally we have to do a bunch of stuff with pay, compensation, and reject request. So that's how you should look at this. So if we do that, so if we traverse the leftmost, and I'm going to use the red color again to highlight this, if we traverse the leftmost line of the sequential operator, we observe the register request activity. Right, so basically this tree tells us, well, first we have to register the request. Okay, then we've done actually everything that we can do in that part of the model, and that's exactly the same as saying, okay, I'm going to flow through this first part, and I see that I have to do the register request. Now I'm going to go into the second child, and that's a more complicated child, because the second child says, you know, actually there's looping behavior here. And how you should read this looping type of behaviors, which is referred to as an XOR loop, simply loop, is these are in pm4py always vertices that have two children, right? The first leftmost part is something you always execute, right? The second child, I'll use again a different color to highlight the second child. So this is the second child, is optionally executed. So you always have a choice, exclusive choice to decide to do that second part. But if you decide to do that, you have to do the first part again, right? So let's do that again using a different color, orange in this case. So I'm following this first child. That's what I always need to execute that. That's the sort of semantics of this XOR loop operator. I see a sequence operator. Okay, sequence was first doing its firstmost child, then its secondmost child. So let's do that. Actually, how you should look at it is in the orange part. I kind of said, okay, I'm starting here, and now I'm entering this plus sign, and that plus sign is actually the equivalent of this AND node that you see here. And obviously, like in the plus sign, like this diamond with the plus sign, where we would say, okay, we have to go up, but we also have to go down. We have to also follow this check ticket because it's a concurrent operator. Here we have to do the same. So in the AND node, we have to assess everything, and we have to complete everything to complete the AND node. So if we go down in this AND node, we see, okay, there's this check ticket activity. That's what we always need to execute. But at the same time, completely at the same time, I see an XOR, exclusive OR node. That's a choice that I also need to execute, right? And I either do one of those, but never both. So either an examination, a thorough examination, or examine casually. So what you see basically is this also known as this subtree here, represented here by this XOR in yellow, directly corresponds to this block over here. And the purple check ticket is actually directly corresponding to this over here. And the orange AND operator basically is capturing this whole block here. Right, so in a way you could see this process tree is some sort of blocking all kinds of, grouping all kinds of behavioral structures together. We have this decision here. I'll just highlight it with the gray point. That's obviously always follows that concurrent block. Like you see in the bottom, the decision is always following that block. And then we are done with this leftmost child of this XOR loop. And then we, as I said, we have the option to do the reinitiation, just like in the model. So if you decide, okay, I do the reinitiation of the request, then you have to again go all the way to this leftmost subtree, as it's called, of your XOR loop, which is exactly the same in the process model, right? If you go through this reinitiation of a request, you end up before this parallel orange block, and you have to again do the parallel block. Then finally, if we at some point we reinitiated a few times and we are done, we go back all the way to the sequence operator. We say, hey, we have also executed our second child. Now let's go into the third child, and which is simply a choice. We have seen that before, right? Same type of operator between the rejection and the payment, right? So this block here with this choice construct on top is basically the block here below. It's important to note that obviously, as I said before, the inductive miner or any process discovery algorithm doesn't know the model below, right? I just use these models to sort of visually compare, okay, this is how you should interpret this process tree. You have to go from top to bottom, and actually the type of operator that you see determines also how you need to go from top to bottom. Do you sometimes because sometimes you have to, if it's a sequence, you have to actually go first left, leftmost child, second child, thirdmost, fourthmost, until the rightmost child. And in other cases, you have to, for the AND operator, you have to execute everything. And for the OR, you only need to choose one specific subbranch, right? It's just, I'm showing you this to show the relation that the process tree has with respect to the BPMN. Then it's time to look at the discovery of Petri nets, which are again another process modeling formalism. Again, fairly simple. Petri nets are easily obtained, like BPMN. A process like BPMN also. Process trees are some sort of subclass of Petri net. So you can actually obtain a Petri net by taking the process tree that you've already learned by using the inductive miner, and then basically just passing it into a converter. So if you type pm4py.convert _to _petri _net, and you give that a process tree, it is going to automatically convert it. You can also try to give in BPMN models, and they will also be converted to Petri nets, but that conversion might not always be 100% correct, because in general, there's such back and forth conversions are not always theoretically possible. The example here, so if you, in that sense, if you do this, you obtain the exact same model as if you would discover the Petri net using this structure. Sometimes the layout is different, although it's the exact same algorithm. So if you look closely, you see that the layout of this algorithm, this Petri net is a bit different than the one before. This is a layouting issue. The Petri nets themselves are actually identical. You can directly discover a Petri net using pm4py.discover _petri _net _inductive. The only difference is that the function here wraps around discovering the process tree and then applies the conversion. So Petri nets need a bit more practice to, be understood, and they are a bit more complicated. In general, the idea is though that you have this net and this graph. In general, it's the case that it consists of circles, as you can see, and boxes. Boxes always represent activities, and in certain cases you see these boxes that are completely black. That implies that such a box is actually an activity that you would not observe. So it's actually it's unobservable transition. You use these type of unobservable transitions, for example, to do a bit of routing. So to enable concurrency, that's a typical use case that you would use that. If you look closely, all the non-black squares here have also a label, and these labels they represent basically the labels that we've seen before: registration of request, examination, thoroughly, casually, check the ticket, initiation of request, etc. So how you should try to read this is that these places, these circles, we often refer to them as places, and these boxes, they are transitions. And the places, we use them to represent the state, and the transitions, we use them to manipulate the state of the Petri net. You also notice, if you look closely, that a place, so a circle, is never directly connected to another place, right? It's always a box transition in between, and vice versa. So what you never see is any arc like this. This is basically not okay. You always have to put a place in between. Okay. As I said, I'm not going to discuss this in too much depth, because usually when I give lectures on this, spend quite some time on explaining it. So explaining that within 5 minutes is really too short, but I'll explain the general idea. what I can do is I can basically put literally a token or a chip, if you like, in a place. I could put a token in this place here. Now, the idea is that when a token is in this place, I might be able to execute, which we call fire, a transition. And in fact, I can execute a transition, and I'll try to draw that like this. So if I have a box that has a bunch of these circles connecting to it, and they all have incoming arcs, if all of these different boxes, all of these places, if all of them contain token, then I can fire this transition. TR stands for transition. Okay, so if I look in my beautiful model here, I see that there is exactly one box, one transition that has, for all of its incoming arcs, it has one incoming arc, has a token, right? I just put the token in this green place. Then I can fire it. What happens if I fire it? I consume all the tokens that are in this input. And for every outgoing arc, I generate a fresh token. And that statement is very important because you should never look at the past in a way. So for this transition here to generate tokens, that's completely independent of the tokens it consumed. It's just if it has all the tokens it needs, it will take all these tokens. You should think of it, throws it away in the trash bin, and starts just generating new tokens. So they can really generate as many tokens as they want. Okay, so now if you look closely, you see again, there's exactly one transition available or in this net that is actually enabled, that can fire, that can be executed. That's this black transition, because that's the only transition. Of course, the token in this green place is now gone. That's why I put this red arc on it, or this red cross. It's no longer there. So if I fire this black transition, I remove this token. That token is not there. And as I said, for every outgoing arc, I'm going to generate a new token. So I generate one here and here. And now it's actually interesting, because now if you look closely, you see that there are three transitions enabled. And what's so interesting about this is that the enablement is independent. So the ticket check can take the token in this place here. It needs the token in this place here. The examinations, they both need a token from the place here. So what I mean is, if let's say I decide to fire the ticket check, that means I drop the token because I check the ticket check is consuming the token and it's starting to produce a token here, right? That it happens completely independently of what happens to the examination. Here I have to make a choice, right? I have to make a choice between examine thoroughly and examine casually. So one of these two can take a token. Let's assume we take the casual examination. And so the casual examination now consumed the token. There's no more token there, and then produces the token, right? So it's very important to notice that this construct that you see here, you see a place with multiple outgoing arcs. On the left, you see two transitions connected, and you see then a place with incoming arcs. This is the equivalent of this this choice, split, and a merge that we have seen in our BPMN model. Here it's a bit more tricky. So this black transition that we've seen, where we have basically two outgoing arcs, is the equivalent of our parallel split in the BPMN model. So to continue one example, the decision is now enabled because it has both of its input places has a token. So you can remove that token, and token is here. Now, for the sake of the visualization, let's assume we take the second invisible transition, black transition. So observe that there's actually two enabled transitions here. We can fire the reinitiation request, or we can take this invisible routing transition. Let's assume we fire the invisible routing transition. Well, then we get into get a token here because it generates a token there. And again, we see a choice between the reject request and the pay compensation. So as I said, I'm not going to fully explain Petri net theory. That's way beyond any type of tutorial like this, but just to give an idea. These are very, this is a mathematical model that allows you to compactly represent concurrent behavior in a discrete manner. If there are certain extensions of Petri nets, for example, Petri nets with reset arcs and inhibitor arcs, that those are a slightly more complicated way to still determine whether you can or cannot fire a transition. And in fact, these type of models are actually shown to be Turing complete languages, so basically the equivalent computational model of modern computers. What I've previously shown you already is that actually these two models are describing the same behavior, right? Where this guy is, but related to that guy is related to that guy is equivalent of that guy is the equivalent of that guy. The decision is a bit of a problematic one because it's at the same time the equivalent of the concurrent join, but it's also, of course, the equivalent of the choice of the decision. Here you have also in the process tree, because this is consequence comes from the process tree, you see that the split here, which splits three possible choices, is actually split up in a set of one choice here and one final choice here in the pattern. But it's exactly the same behavior. There are some other discovery algorithms also implemented in pm4py. The alpha miner and the alpha plus miner. The alpha miner was one of the first algorithms, not the exact first, but one of the first algorithms that discovers some form of process model from event data. Alpha plus miner is a simple extension. In this case, if you run those models, you see they are not going to find these invisible transitions, these black transitions. They are not it's not possible for these algorithms. That can sometimes already lead to problematic cases. Here I see you see an example. The invocation of these algorithms is exactly the same. You type pm4py.discover _ Petri _ net _ alpha _ plus. These Petri nets, or the discovered Petri nets, that's something that I did not mention yet. They do not only give you this net object, so this graph object with the places, with the circles and the boxes. It also gives you what is known as a marking. That's an initial marking and a final marking. And basically those are the intended initial state. So where do you put your initial token? That's your initial marking. And the final marking is actually the target final state. So that's often it's one place that should in the end contain a token, and then the process is finished. Again, if you want to have more information on this type of theory, either look at the MOOC of process mining that is given by Professor van der Aalst. You can also type comments that you would really like me to create a theory session on Petri nets, and then we do that. Okay. Briefly, discovery of process maps. If you look at a lot of commercial tools, you see that they do not use BPMN process trees or Petri nets. They use what they typically call process maps. We like to call them directly follows graphs. I'll give you an example. If you take our example data, you learn a discovery directly follows graph, you'll get a graph that looks like this. In this case, we have a specific start and end point, and we highlight that by drawing a green circle and connecting that to all the activities that ever, in any case, start the case. and we have an orange circle, and we connect that to every activity that finalizes a case in the data. And as you see, of course, in our example data, the register request is always executing, is always being executed, and the reject request and pay compensation are always executed at the end. You see an overlay here where on the edges you see how many times a certain activity is followed by another activity. So what do I mean actually with that? If you see the register request and you follow that to the examine casually, you observe that apparently in 3 times in this log, there was examine casually was followed, or was following the register request activity. And then I can follow this edge and I see in 4 times the check ticket was being executed after the examine casually. Now this looks nice, but there's one big problem with this process map, and sadly a lot of people don't know that actually use these process maps, is that this is just a graphical visualization of local relationships, right? Every edge in this graph represents a local relationship between one activity and another activity. So if you look closely in this graph, you see a lot of cycles. You see that the examine thoroughly can be before and after the check ticket. But if we've seen before, that's actually only the case if there's a reinitiation in between. So the examination, the fact that in this model, and I'm talking basically about, for example, this connection here, the fact that in this model, you see these connection going both ways. You also see the same behavior between the casual examination. That's because of the concurrency. So this concurrency that allows us to schedule these activities in arbitrary orders will naturally lead to these cycles in this type of process maps. This is not a problem, it's just a fact of life. So what is a problem is that a lot of people, when they see this graph, even for the simple model, think that the process is not structured at all. But as we've seen, the process is very structured. So that's a false conclusion that 95% of people that is applying process mining based on various commercial tools actually falsely makes. And what's the problem with the false conclusion is if you then would like to reorganize your process because of this observation, you're doing something completely wrong. Point being, these models are not useless. You can still see local relationships. So you can see what is most common, which activity is following which other activity most commonly, etc., etc. And that's all what is there. But you have to just be very careful to try to reason from the end to the end, because you'll see all kinds of connections and paths in this graph that are in reality just simply not there, because you're combining local relations of different traces with each other. As an alternative, we also have heuristic nets in pm4py, or heuristics map, if you like. That's actually an algorithm that tries to first learn the graph that we've seen in the previous example, but then tries to reason on which activities are concurrent. And it will not connect concurrency. So this is particularly trying to make a process map where causal relations are being present. And you see also the difference, right? So you see that the check ticket in this case is not at all connected to the examine thoroughly and the examine casual. That's the main difference. So in that sense, it's even advisable when you try to learn process maps to also always try to take a look at these heuristics maps, because they are actually trying to push away this concurrency cycles. Okay, quickly about handling noise. It's very simple, actually, so we'll not spend too much time. I created a broken event log where some activities are missing, etc. If you load that data and you learn the BPMN model without any form of filtering, well, you get a model where, if you look closely, you observe that a lot of the activities are now, we can skip them, right? All kinds of skips. Skip. These are all skips. And then, so we can skip everything, but then we can go back, right? This is typical behavior when there's noise in the data. You get process models that describe, actually, in a way, they describe that everything is possible, because you can decide to do something or not. a number of times and you can go back. So you can actually create arbitrary cycles of arbitrary behavior. It's very difficult to get meaning out of this. Of course, you can use the filters that I've shown in previous demonstrations. But certain cases, there's types of noise that are even not easy to detect using out-of-the-box frequency-based filters. So for that, there's also filtering mechanisms built within the algorithms, for example, in the inductive miner. And that's very easy because you can just basically use the same invocation that you would normally use for the discover BPM inductive, but you just add a frequency threshold. And I think in this case, the higher you set the threshold, the more rigorous there will be filtering. And what you can see is that on this noisy data, we get the model that we see in this particular slide. Now, this is not the model that it really was. If you would look at the original process model. So it's, of course, I've used data with noise. At the same time, this is a much better reflection of the real process model versus the previous slide. So in general, when you have real data, specifically when you have real data, make sure to also consider a bunch of threshold values to see if you can get to more reasonable process models. About how reasonable process model is, we can also talk in another tutorial where we will talk about conformance checking. Right, some final quick thoughts about process discovery, and then I'll wrap up today. Because I've shown you process discovery, and for the purpose of this demonstration, I've been only using very simple dummy data. However, when you apply this on real data, and if you go to processmining.org, you can actually find some real event logs available from real processors, real companies, just for free, open to download. So go to processmining.org, go to the event log section, you can find logs there. If you apply, and whether you use pm4py on any other process mining tool that at least can also discover models, you'll see that a lot of problems are going to be there. You will not get models that are so beautiful as the example that I've shown you. And I'll try to explain you a few reasons why this is the case. And reason number one is best reflected by the picture that you show here. That is that if we build a process model like the model that I've been using today, we tend to reason on a high level, actually an abstract business level. So the activities like the registration and the check ticket that I also have in this example, those are the activities on the high level that we want our process to perform. However, it's very likely that the systems that record events that are related to that process, they record those events on a much lower granularity. So it could be that the registration of the request is actually executed like I've shown here, like this regact start, opc, pp open, regact end, system level events that together form the register request activity. And the same for the check ticket. And the point is that in this example image, we're actually showing, okay, we assume that these low-level events happen in a strict sequential order, but of course that's not necessarily the case. It can also be that in certain cases, these two events here can be swapped within the registration request. So when you look at applying this in practice, you see that in a lot of cases, there is one cause of many causes that makes it very difficult, is that there's a data granularity mismatch between the level at which we would like to reason on the process versus the level of tracking. Another problem is that I would like to call is that there's no contextual activity differentiation, or in other words, no label splitting is applied. The best way to explain this is by using our day-to-day routine. Let's assume I model my day-to-day routine and I'm now using a process map style visualization for sake of simplicity. Let's assume that every morning I first take my breakfast, then I go into the shower, and finally I brush my teeth. And I record my behavior. I'm trying to learn a model based on my behavior. Now, of course, we do all kinds of things during the day, right? I haven't modeled that here. Now, the problem is that certain days I go and do sports. I go running, I go cycling. So I also take a shower in the evening. Now, all these process discovery algorithms, they don't differentiate between the first, second, third occurrence of a certain activity in a certain trace. So they will map every activity of the same type onto the same, transition activity in the model. So actually, if you do not differentiate, you would get models that resemble what we've seen before, where after the breakfast, you take a shower, but then you are not always brushing your teeth because, for example, in the evening after sports, you usually first take a shower and then you have dinner, right? So by not splitting certain activity labels into shower number 1, shower number 2, because contextually, whenever we do that activity is very different from the other activities, you'll get models that are often containing a lot of skips and loopbacks, because you're trying to map contextually different activities on the same activity instance, right? So if I would differentiate that more clearly, you would get models where I basically say, well, I actually have 2 shower activities. They have exactly the same activity name, but they somehow are different instances. As I said, it's known as a label splitting problem. Then activity durations are ignored. We've seen that in the example data. We just have this completion time, right? You only have the completion time or start time of one event activity, but you don't have the duration. And this is also problematic because in real life, of course, activities like you see here in the right-hand side of this picture, activities tend to have a duration. Even if it's a system activity, it has a few milliseconds of duration. So if you would start recording the start and end of activities, there's no longer the notion of a total sequence over the activity instances that you see. Rather, there is what is known as an interval order, which is a special case of a partial order that you see on the left-hand slide. So instead of having finite total sequences of activities, when you take effective duration into account, you all of a sudden work with partially ordered instances of activities. And a lot of algorithms simply do not really work if you have that data assumption. So that's another tricky thing, specifically if you would like to do accurate performance measurement, you have to take start and end activities into account to, for example, differentiate service times from waiting times. And then there's the ignorance of domain knowledge. To give you a final example, there are open event logs where the most common variants of the execution of the process are execution that you do not want to have. For example, people that don't pay a fine. Most often people don't pay a fine. They simply don't pay, or we need to send people to collect the credit. There's actually real event data that shows that. So these type of techniques, they tend to, most of the techniques that we have tend to be completely automated. And it's the question whether you really want to have completely automated process discovery techniques, or whether you would like to have, let's say, computer-aided modeling type of techniques, where you can model process models in a digital editor, and you can be guided by the data. So actually what we're working on is a prototype tool that can exactly do that, called Cortado, and it allows us basically to, on the one hand, model, you see it's a process tree in this example, we are able to model this process model, but we're supported by the data. We can check whether variants of the process fit. We can let this tool itself figure out how to automatically update the model with new data, etc., etc. And I think the ability to integrate domain knowledge, so knowledge about the process that simply people that work with the process day to day have, is very beneficial to create accurate process models, because you don't want to learn a process model that describes all behavior. The actual end goal is to find a process model that accurately describes the ideal execution as supported as much by the data, is my view. And that's it for this tutorial. Thanks for watching this tutorial, and hope to see you next time, where I most likely am going to talk about conformance checking and pm4py. Thank you.